So I'm going to talk about correlation enhanced electron-phonon coupling in this famous FeSe STO at a magic angle. Now, this angle has nothing to do with the twist angle. So this is some, we'll see that why this angle is called magic angle. And this is based on this, this archive preprint. First, I would like to thank my former postdoc advisor, Christian Holle at Rutgers. And this work was done in collaboration with experiment here at WVU by Lian Li, who grew a lot of single layer iron chalcogenide on STO substrate, as well as they measured the R-pace. They did they did measure the superconducting gap using STM. And most of the calculation is done by Antik Shihi, who is a postdoc here. So, as you know, this figure that how the TC is going with time, you might be wondering why I'm putting Thomas Edison's photo, because so far it has been kind of trial and error basis, Edisonian approach, except in recently in the hydrides that that was kind of predicted using electron-phonon coupling through density functional theory. So about like 14, 15 years ago, this iron-based superconductors are discovered, and it has various kinds of, around 2007 or 8, it was discovered. And eventually, in the last 10 years or so, there are various kinds of bulk iron-based superconductors were synthesized and characterized. The Fermi surface here has this electron pocket and hole pocket, mostly T2G orbitals. For the simplest one is a FeSe with TC is around 7 Kelvin. With pressure, it can go up to, say, 30 Kelvin. And immediately after the electronic structure was understood, the pairing symmetry and the phase diagram was kind of obtained, that it has ground state of spin density wave, followed by some nematic order, and the superconductivity arises upon electron or hole doping or by pressure. And based on the Fermi surface, there are pairing symmetry that started evolving and debated, and mostly now it is settled with S plus minus with positives with different sign on electron and hole pocket. Now we also saw very interesting observation. This is an empirical observation. If we plot the TC with the measured TC in the experiment with this pnictogen angle, the angle that controls the height between iron and the chalcogenide, that has a very critical behavior, that it goes to some magic angle where the TC is found to be highest. Now, we also learned that this the origin of the electron correlation in these compounds are not Hubbard-U, but Hund's coupling. They're often referred to as Hund's metal. It tries to make parallel spin. And there's a nice review article by Antoine and his colleagues on this Hund's coupling. And the measured large fluctuating moments was actually confirmed right after, confirmed in DFT plus DMFT. This was the work from Rutgers. And this is the reason behind, the Hund's coupling is actually the main reason of this mass enhancement. And then we also learned that with zero Hund's coupling, we see kind of LDLI behavior with the resistivity, with temperature. But if we start on the Hund's coupling, then at high temperature, it is quasi-linear, goes to incoherent bad metal, and low temperature becomes Fermi liquid. And this was later on also confirmed from the experiment. So this coherence-incoherence crossover was also discovered for this bulk class of iron-based superconductor. And then this monolayer on STO was grown and got a lot of attention because the TC was surprisingly high, almost 1 order of magnitude high. And as I was saying that in the bulk phase, there is a phase diagram where the ground state there is kind of nematic order suppressed with the superconductivity. But if we look at a monolayer, we still don't have any antiferromagnetic order. There is no nematic order in the single layer. What we started seeing in the literature is a lot of signature from the experiment of the interfacial electron-phonon coupling. For example, this work, let me see the pointer. This work from Z-Exchange group showed the replica band, which is kind of responsible for the oxygen motion in the STO, but which you cannot see. They could not see it in two-layer and multi-layer FeSe. And very recently, from electron loss spectroscopy, again there was signature of electron-phonon coupling at the interface. Now, if we see from bulk, if we do electron dope, the TC can be raised, but further it would be raised only when it was grown on substrate. And if we look at the electronic structure, the Fermi surface, it has the whole pocket for the bulk. But it was surprising in the beginning that for the FeSe STO, this whole pocket was missing. So this conventional S plus minus pairing symmetry was under question. So naively, if we look at the electronic structure of FeSe bulk, there are electron pockets and hole pockets. Of course, there are multiple pockets. And for FeSe STO, the whole pocket is down. That means there's some electron doping happening. And if we just calculate DFT band structure for this FeSe on STO lattice, we do see that there is a whole pocket. But if we remove the oxygen on the titanium oxide, this oxygen vacancy, that can donate electron and actually make this whole pocket disappear. And this is a work actually we did it with Charles Ahn group where they had done a high energy X-ray and actually figured out that there are double TiO2 termination on the STO. And even in the double TiO2 termination, you need to have oxygen vacancy to not to see the whole pocket in the RPES. So it's kind of obvious that there is a charge transfer from the substrate to the film, and the other possibilities might be excess titanium in the substrate. Now, the central question is why the TC is so high. Okay, the first thing is that we would like to know whether the electronic structure is really different from the bulk or not. Okay, and then we do see the charge transfer from the substrate to the film, and there are electron-phonon coupling. Are they helping each other to enhance TC? So the answer is yes. The charge transfer process and electron-phonon coupling is actually helping each other. And I'm going to show today that this was done through the electron correlation, which is controlled by this angle, the Nicotogen angle. Now, in this audience, I don't have to really tell what is DMFT, so I'm skipping it. But the code that I use is developed by Christian Holle. This is a self-consistent DFT plus DMFT software, where the lattice problem is described by Wien 2K, all electron basis, and the many body problem is solved. It's a single site many-body problem is solved using CT-QMC. There are few key features I would like to mention here, is that it has full charge self-consistency. We can get exact double counting in the DMFT functional. The free energy functional is stationary here, and there's no downfolding. And for that, we can get accurate total energy as well as force, which will be important for this talk. And very recently, we are also doing high throughput DMFT. We have done high throughput DMFT. And then we are also exploring how to get the Hubbard U through constant DMFT using this same code that is used to calculate the electronic structure. And I'm going to deviate a little bit from the topic and show how we are doing this, calculating this U. This is again the Hubbard model everyone knows. Is this U is the difference in the energy of adding one electron and removing one electron from the site. And traditionally, it was by calculated using constant LDA, where the hopping is constrained, the occupation is also constrained. And then it was later on modified with the linear response approach. Nevertheless, the U is, that is a tuning parameter. It depends on materials to material. And then there is also quite famous approach is constant RPA, where we screen the screening. There are advantages of CRPA, that you can get the full matrix, the frequency dependence, and it can be on site and intersite. But the difficulties is for metals, it is quite difficult to disentangle bands, and it depends on the energy at the window. And most importantly, this U is material dependent as well as method dependent. So if you want to calculate electronic structure in a particular method, it is better to calculate the U in the same method. So this is what inspired us to calculate the U through constant DMFT, where we actually calculate U's very similar to the CDFT, except the total energy is now the DMFT energy, which is a functional from obtained from Luttinger-Watt functional. And this process, we actually can include vertex correction. And as we are saying this, most importantly, the U is obtained in the same method that we are using to compute electronic structure. And I'm just going to show one example that it can actually capture the metal insulating transition in B2O3. If you calculate the U for the metallic phase, you get around 6.8 eV, and quite large U for the insulating phase. And the spectra matches quite nicely with the recent experiment. So this is something that is coming up soon. In this method, one can calculate U, and for FeSe, it would be around 5 eV. Now, as I promised, I'm going to show how to compute the electron-phonon coupling. So traditionally, it is calculated in DFT routinely, this electron-phonon matrix element. And using frozen phonon method, using the supercell calculation, it boils down to the deformation potential, where this deformation potential can be obtained by taking the ratio of changing the energy with as we move the ion. And this particular mode that we are interested is the A1G mode, because that controls the angle. And in principle, one can get all the various modes in this supercell calculation and compute the electron-phonon coupling. So the way that we did almost 10 years ago is this frozen phonon calculation, through frozen phonon calculation. Again, these bands are DMFT bands. That means they already include the correlation effect. In this particular case, originated from the Horn's coupling. And as we move the ion, if we move the ion a little bit, then the band would move, and the ratio is the deformation potential, which can be equated with electron-phonon coupling. So the first thing before we do to electron-phonon coupling calculation is to find out the equilibrium position. So back then the force was not implemented, so I had to do it manually, and this was done using LDA and GGA, as well as spin polarized CGA and DMFT. And DMFT is, of course, very close to the experiment, but you can see that including magnetism actually improves the LDA. So the LDA tries to overbind, so the separation and this angle determines the separation between these two layers. They are quite close to each other in LDA, and in DMFT it is close to the experiment. Then we move the ion and we try to and we compute the difference in this in the spectral function. Here you can see almost these thin lines are DFT bands, and these thick lines are DMFT spectral function. You see almost 3 times higher deformation potential compared to DFT, giving the same amount of displacement here. Now, later on, this was experimentally verified by Z-Exchange group, where they first measured this directly in the experiment, where they have done 2 things together. One is time resolved RPS, and another is time resolved X-ray. So that from the time resolved X-ray, one can get the motion of the atom, and you can keep track of the position and as it is vibrating here. And then you simultaneously send UV light to get the RPS, so you can get the band moving. And they were able to lock into a particular mode. This is A1G mode, and able to measure this deformation potential. And they compared with our calculation. Turns out this atom position, the frequency, and most importantly, the deformation potential is quite matching well, and it's almost 1 order magnitude higher than DFT. And very recently, there are a lot of calculations coming out from Flatiron and on the oxides. Now, going back to the correlated electronic structure. So here is the quasi-particle weight for the bulk, FeSe bulk phase, and then this freestanding monolayer, which still doesn't exist in the lab, but we can do it in our computer, and then FeSe on STO, and then the oxygen vacancy, because that is important for the charge transfer. Now we can see that the correlation strength actually follows this angle, which I'm plotting on the right. And the hybridization function is actually also following the same trend. The FeSe STO with oxygen vacancies, making things really correlated. And if we change the Hund's coupling J a little bit, the mass changes a lot. So again, the Hundness is intact in the monolayer compound. We also see the coherence-incoherence crossover similar to what we see for the bulk pnictides. By extrapolating the imaginary part of the self-energy to 0, we can see that at particular temperature, for bulk and monolayer and the FeSe STO went to the coherent limit, but the oxygen vacancy, the coherence temperature is different. And if we just calculate this spectral weight by as a function of angle and make a fake FeSe with the angle of the bulk, which is known from the experiment, you see that it's following linearly. That means going from 3D to 2D, the only one structural parameter that is controlling the strength of correlation is the angle. So this was kind of in 2017, and we discovered that there are double role of oxygen vacancies in STO. One is to increase the correlation in the FeSe STO, and also doing the electron doping to the film. And this oxygen vacancy in STO is actually controlling the angle, which is changing the correlation. Now, this tuning of this angle is actually was very interesting when I talked to my colleague here, that they were able to grow FeSe monolayer on different type of substrate and saw the superconducting gap, measured gap, is quite different. And then we computed the angle. Turns out the angle is also quite different. So there must be the correlation and the angle and the measured TC is related to each other. One can actually shine UV light and change this angle as well. I'm not going into this detail, but how we can manipulate this angle, apparently, this is also affecting the TC. So the route that we took in this work is by doping or alloying tellurium atom and sulfur atom, because they have different radius and you can control the angle. So we did optimize all this heterostructure with various alloying, with tellurium to selenium, and then with different substrate, and then with sulfur, and then 50% sulfur, 50% selenium, etc. And the angles are quite different. And my colleagues, they actually grew this kind of samples, a single layer of various chalcogens on STO. And if we plot this angle with the doping or alloying, you see quite linear behavior. And these black points are where we could not compute because they're quite large unit cell. So we extrapolated from TEM image and using the alloying law called Vegar's law. Now, next thing, what was very interesting is the following. As this function of doping, he also measured the superconducting gap, and the superconducting gap go from no superconductivity in the tellurium limit goes up as we dope or alloy with selenium, and then goes down with sulfur doping, as you can see it from the STS gap. And so the next thing is to plot this gaps, measured gap size with this angle. And again, these angles are obtained from the DMFT calculation with DMFT force for most of the points, except this concentration where we could not reach. We could not compute for the large due to the large supercell. So it shows a very interesting dome. And in my opinion, this is something already, something to appreciate, because you are controlling the gap size with single parameter in the structure file, in the structure. And that's the angle. And we knew that the angle has something to do with correlation, and angle has something to do with TC now in the monolayer limit. There are RPES also done. The RPES looks a little interesting. With FeSe monolayer, there is no hole pocket, as I was saying. And then with tellurium doping, apparently, again, the charge transfer happens. And with FET limit, there is no electron pocket. There's only hole pocket. With the sulfur doping, the Fermi surface doesn't change. There's only electron pockets. Now, if we compare the spectral function and the RPS with these three extreme cases, we see that FET is quite correlated, and the correlation is kind of decreasing with the sulfur doping. We can also capture this charge transfer and the bands in DMFT. And if we calculate the mass enhancement, we do see that the tellurium doping, there's a huge mass, and also the orbital differentiation is also quite large, and the correlation strength weakens as we dope or alloy sulfur. Now, these stars are directly from the RPS. So what I'm plotting is this mass enhancement from the experiment as a function of alloying. So these plots, these blue stars are directly from the experiment, and it is following the similar trend that we are actually seeing in the DMFT. Now, next is to compute this A1G deformation potential for all these monolayer, these interfaces. So what we did is we calculated this only for the film, keeping intact the same angle information for the various substrate, for the various interfaces, and we computed the average deformation potential for electron pocket and hole pockets, and they are in electron pockets and in blue, hole pockets are in red. Now we also know how the Fermi surface is evolving in the experiment. For example, in FET, there is only hole pocket, so I can mark this as our hole pocket, as our experimental Fermi surface. And then for the FeSe, this is the electron pocket, so I can mark that to be our experimental Fermi surface. And if we just plot that, the only experimental Fermi surface that shows the similar dome as in TC goes up and down as we change the alloy concentration, except this FeSe 50% sulfur and 50% selenium. And turns out that in this doping region, the Raman experiment, recent Raman experiment shows that this A1G mode is actually disappears in this particular concentration and again reappears. So this mode is not at all seen. So then we kind of seeing this similar trend with what we are seeing with the gap as a function of the angle, the single structure parameter. And then if we plot the one that was measured directly in the lab for the bulk with the angle, and here is the star, and this has the and the theory value with the maximum deformation potential and the average, it is perfectly aligned. And this was quite interesting to us. And if we compute the same thing with DFT, where there is no fluctuating moment, first of all, the angles are off, quite larger, deformation potentials are quite low, and they do not follow any trend. So if we look at the density of states, in this three region, the density of state at Fermi energy does not change a lot. Although there is no direct way of estimating TC from this calculation, but we can estimate based on taking the ratio from DFT, where assuming that all the modes can actually be enhanced, which is a big assumption, then we can estimate the TC by taking the ratios. and Tc will be around 34 Kelvin. So in summary, we showed that this Nichotogen angle can be tuned with the alloying, and it will show a superconducting dome as a function of this angle, and it picks at a particular magic angle where the electron-phonon coupling also is highest. And since this is Q equal to 0 phonon mode, it can enhance superconductivity either in electronic or phononic origin. So I also have a pictorial summary. So this is weakly correlated electron interacting with phonon, A1G phonon, giving this weakly electron-phonon coupling where, but the measure Tc as a function of this angle shows the dome. But when we consider phonon coupling with strongly correlated electron, we do see this dome, and we kind of seeing this, that the correlation and the atomic structure here is the angle, and the electron-phonon coupling are kind of working in a feedback loop. So thank you very much for your attention.
Yes, floor is open for question.
We have a question in the chat.
Yes, let me read it. So Jennifer Coulter asks, the spectral bands you showed are, as you mentioned, very correlated. If the deformation potential calculation you are doing means you have to calculate the difference in band energy, how are you choosing which place in the band to take that energy difference? The band looks very spectral.
For which one? Let me just go back. Pointer. Okay. So can you please repeat the question? Actually, let me read from the...
Yeah, maybe it's simpler. Read it for the audience, but...
Yeah. Okay. The spectral bands you showed are mentioned very correlated. If the deformation potential calculation you are doing means you have to calculate the difference in the band energy, how you are choosing which place the band to take the energy difference. Oh, okay, right. So we got the spectral function that we can compute, and then we get the Fermi surface. Now, if we take the approximation that that the imaginary part is 0, then we get this normalized bands due to correlation, and then you can keep track of the band. So with this assumption that the imaginary part of the self energy is 0, you can get the renormalized band and keep track of the band. Yes, Antoine?
Yes, I have a question about, which is not perhaps completely directly relevant to the main message of the talk, but it's about the calculation of U from embedded DMFT, right? So the idea is to do a total energy calculation within, say, DFT plus DMFT, and then calculate the second derivative, right? And so you showed values for V203. Can you show them again?
Yes, sure. Go back here. Yes.
And so do I understand correctly? Okay. So one is V203 in the metallic phase, right? And the other one is V203 in the insulating phase. I'm not sure what alpha and beta mean. I mean, it's just a chromium concentration.
Yeah, so thanks for pointing this out. So the chromium concentration that actually changes the structure, and that's actually important. And one needs to actually optimize the structure. Then you have this paramagnetic insulating phase and paramagnetic metallic phase.
Yes.
And you compute separately for U, and you can find the paramagnetic metallic phase, you're getting smaller U, and with that U, you can see the metallic behavior. And similarly for the beta phase, you're going to find quite large U. If we do the same thing with CDFT, they are exactly or very close to each other in these two phases. But if
Right,
you
right, right. But so the symmetry. So this is a difference of unit cell volume between alpha
no,
and beta, or symmetry.
the same symmetry as far as I know, but the angle, there is some, again, there was some
Right.
angle that changes, and not quite a lot, but around 3 to 4 degrees there. And that also is important because, I mean, we wanted to,
This is,
yeah,
but this is
yeah,
a huge difference, 7 eV to 11 EV. This is
yeah,
enormous, right?
right.
Is this, what about constrained RPA, for example?
We have not done it yet. We
Ah.
did it with constant DFT, and they are same for the both phases, around 6, I believe. But CRPA, we have not done it.
So the V203 results are published?
No, it's just in preparation. We're just writing up. So
Okay. That's very intriguing.
yeah.
It looks very large to me, but okay.
Yeah,
And
the
if
large U is actually due to the large window that we use in our DFT plus DMFT implementation. That's what we get. And this U, you know, if we is not very, I mean, the surprisingly, I mean, what we did for all binary transition metal oxide like nickel oxide, iron oxide, over there also we found U equal to 10. And this is and it was quite well matched with the RPS and the photo emission. So this is quite, yeah, it's really large because of our large window, and we have around plus minus 10 EV from the Fermi surface to the window of hybridization in our DFT plus DMFT, and that's the reason of getting a larger U.
And the reason why the gap only changes by 10% when you change U by an enormous amount is because this is more a charge transfer regime, or what? Because it's surprising, no? You go from 7 EV to 11 EV and the gap just changes by, from what I understand. Not the gap, I mean the distance between the low and
yeah, so this lower, this band does not change with this U, but it will be metallic. Of course, you see this band
so
is
that I understand.
charge transfer. Yeah, the charge transfer. Yes.
Okay, surprising. Thank you.
Luca?
Yes. Hi, very nice talk. Can you specify how you extract the experimental mass enhancements from ARPAS?
Oh, this was from let me see, the electron or the electron pocket. So you can get you know, curve fit with the electron pocket and get the curvature. That's how we can get the mass from the ARPAS. This is only on the electron pocket done.
Okay, because you were specifying about this selectivity in the masses, and it's clear that when you have selectivity, you should have like different estimates of the mass enhancement depending on the orbital character of this.
Right. Right. I mean,
There are if you have different ways to estimate the mass enhancement based on the experiments, and when you are very selective, they start to diverge among each other.
I agree. I completely agree. I think we need like better resolution of RPAS for all this film, which we wait to see, and then we can identify the orbitals and get the mass for orbital by orbital. Yes. Yeah,
So
absolutely right.
these ones you say these are Fermi velocities of the electron pockets somewhere.
Yeah. So this is somewhere in this curve fitting of this pocket and getting the curvature.
Okay.
Yeah. That's what is not, you know, exactly matching on the calculation, because we have, you know, if it's averaging it out, but more or less the trend is captured.
Sure. Yeah. Agree. Well, maybe if there's 2 more minutes, I would like to ask where the DFT part of the calculation is what kind of functionalist? GGA, LDA?
We use LDA for the DFT part using bin2k.
Okay, because I think there are evidences that since in all these iron-based superconductors, which are in some sort of semi-metals, the overlap between the electron and hole bands is slightly overestimated by these methods. So that typically when you have several sheets in the Fermi surface, you have typically two large pockets. And I think it was understood that if you reintegrate some kind of Hartree-Fock treatment of the non-local exchange, you get the size of the Fermi pockets typically back to what experiment give you. So in the estimate of how you make disappear the whole pocket, maybe this has some role to play, using hybrid functionals or Hartree-Fock corrections to.
Oh, right. I mean, I agree with you, except the hybrid functional. So we actually did hybrid functional. It turns out to be disaster for even bulk. It shows gap even. Some certain bulk.
Because there are parameters in hybrid
right.
functionals, and one should not just trust blindly.
Right. No, we tried actually
for
screen
some
hybrid. Right. We actually tried two different types of hybrid for simple sodium or potassium metal, and we saw that it was the worst, even worse than LDA for metals, so the hybrid. So the hybrid functional, I don't think that would help here. But even spin polarized GGA is actually better. But unfortunately, the spin polarized GGA would give you a completely different Fermi surface.
Sure.
Yeah.
Okay, thanks.
Subhasish, let me ask you a trivial question. Why is your perfect magic angle 107? Naively, I would say it should be 109, like the perfect tetrahedron. Why it's 107?
Yeah, this is the cost of going from bulk to STO heterostructure. So the lattice parameter here is actually the STO lattice parameter that we used, which is seen in the experiment. And I've talked with many experimental colleagues there. If it's a single layer film, it actually goes to STO lattice parameter. So the lattice parameter is different. The angle is also different. So the cost for going from bulk to on top of STO is the reason of the change here.